In this video, we're going to briefly look at the concept of equilibrium points. And given a differential equation, dy dt equals f of t comma y, remember all this notation means is that dy dt can possibly depend on both t and y. So in other words, the right-hand side could have at most t's and y's in it, although it doesn't have to. It could just have only t or only y, or it could even be a constant on the right-hand side. So remember, this notation just means that can have t and or y. Okay, so given that kind of differential equation, an equilibrium point is any value of y, okay? Keep that in mind. It's not a value of t, it's the value of the dependent variable. So if this was dw dt, it would be values of w that make the differential equation equal to 0 for all time. Okay, that's key here. So when you think about equilibrium, if something is in equilibrium, there's no net change in it. So if population size is in equilibrium, that means that from one year to the next, the size of the population does not change. So maybe people are born and people pass away, but in net there would be a 0 change. And so that means there's no change in that population. And if that were consistent for all time, then we would say that we are in an equilibrium state. Okay, so that's key here. It's the value of the dependent variable for which dy dt equals 0. Okay, so let's take a look at an example. Find the equilibrium point or points of dy dt equals y minus 5. So I want to know for what value of y, does dy dt equal 0? Well, you can do this algebraically, or you can see that if y is 5, 5 minus 5 is 0, and then dy dt will be 0. Alternatively, you could substitute in 0 for dy dt and solve for y. Now here we get y equal to 5. And so that means that y equals 5 is an equilibrium point. Okay, so here's the idea that if y is equal to 5, let me kind of sketch a little graph here. If this is y versus t, and let's say that our initial condition is y of 0 equals 5. Okay, so we start off with 5 million elk, let's say. And then what's going to happen? Well, in 1 year, to figure out how many elk there will be in 1 year, we plug in our current value of y, which is 5. 5 minus 5 is 0. So the estimated rate of change per unit time is 0, meaning that in 1 unit of time, we should have 0 change. Now, at time 1, now we say, well, what's the rate of change going to be when y equals 5? So we plug y equals 5 back in. We get 5 minus 5 is 0. We get dy dt is 0 again, meaning that over the next year, or next unit of time, there's 0 change again. And you can see that anytime we plug in y equals 5 in this equation, the dy dt, the elk per year that we get, will always be 0. And so without having to do this step by step, we could indicate that when y is equal to 5 for all time, the rate of change will be 0, meaning we'll have the same population size. Okay, great. So now that we have that concept, let's look at one that involves both y and t. Now, it's not always true that you'll have equilibrium points, but the way to check is to solve for the value of y that makes dy dt equal to 0. So here I can actually, if I factor out a t, and I get t times y minus 3. And you can see that the only way that you can multiply two quantities and get 0 is if one of them is 0 or the other is 0, right? So a little review here. If a times b equals 0, then a equals 0 or b equals 0. But one of those statements has to be true. The only way for a product of two numbers to be 0 is for one of those factors to be 0. Okay, well, t is not always going to be 0. For an instant, t will be 0, and then you'd say, well, isn't that an equilibrium point? Well, no, it's the value of the dependent variable that makes dy dt 0 for all time. So t equals 0 can't be an equilibrium point by that logic, because t equals 0 is just one moment in time. However, if you notice in the second factor, y minus 3 equals 0, if y equals 3, well, it doesn't matter what t is, right? If I insert 3 here, 3t minus 3t is always 0. Doesn't matter what the value of time is. So y equals 3 will always be an equilibrium point. Now, this isn't part of one of these examples, but let me just illustrate one with no EQ points or no equilibrium points. Well, if dy dt was, say, y minus 3t, okay, the only difference here being that the first term doesn't have a factor of t. And if I try to do the same thing and say, oh, I'll just solve for y, so we get y equals 3t. But notice that the value of y, this is changing at each moment of time. Right? So y cannot be, this is not an equilibrium point because it's not a value of y. It's infinitely many values of y depending on what the value of t is. In fact, we could even argue that the only time this will have an equilibrium point is when t is equal to 0. And then when t is equal to 1, the value of y would have to be 3 times that, and so on and so forth. So, no equilibrium points if your value of y depends upon time. It cannot depend upon time. Let's get one more. The equilibrium points of dy dt equals y squared minus 3y. Now, a lot of times you can still use algebraic techniques to solve equations because ultimately, although this is a differential equation that we're solving, whenever we insert something for dy dt, it becomes a simple, I shouldn't say simple, but there is no calculus anymore. It's just an algebraic equation now. Now, in this one works out nicely, but I could solve with quadratic formula or plot the parabola x squared minus 3x and figure out where it crosses y equals 0, where its x-intercepts or horizontal intercepts are. But this one factors, I could factor out a y and make this y times y minus 3. And the reason I like that factorization is because, once again, this comes back to this principle here, that the only way this will be 0 is if y equals 0 or y minus 3 equals 0, which implies y equals 3. So this one actually has 2 equilibrium points, meaning that if I were to look at t versus y, if y is equal to 0, kind of by the same logic as our first example, where y was 5, then dy dt, if y is equal to 0, then dy dt will always be equal to 0, and we will get no rate of change. I'm trying my best here to keep a straight line. Okay, that's y equals 0. And then if your initial condition were to be y equals 3, then that would also mean the population is the same for all time. Now this is great, but we might also want to ask what happens above, in between, and below. Right? So we actually have sort of 3 regions in this graph. We have, I'll call this region 1, region 2, and region 3. Well, you might remember from calculus that if I have a graph, the only way a function can go from increasing to, say, decreasing, assuming it's continuous. A continuous means there isn't a hole in the graph or there isn't an asymptote of some sort. The only other way for this to go from positive to negative slope is, well, it has to reverse directions, right? It has to come back down, which means there's a moment where the slope is equal to 0. So we propose this theorem, which is kind of supported by this concept, given an everywhere continuous autonomous differential equation. Okay, so we're only focusing on the ones that only have y in it. The sign of dy dt can only change whenever dy dt reaches 0, right? So here we go from positive slope to negative slope. The only way for that to happen, if it's everywhere continuous, meaning there's no breaks in the graph, no asymptotes, nothing like that, is if dy dt reaches 0. In other words, the sign of dy dt will either always be positive or will always be negative in intervals surrounding values of y, for which dy dt equals 0. So in example 3, we have 3 intervals. We have region 1, which we can think of as y being bigger than 3. We have region 2, which is y is between 0 and 3, not including 0, not including 3, because at 0 and at 3 we have equilibrium. And then the third interval is y is less than 0. Okay, so let's look at the sign of dy dt. So the beauty here is it's sort of like the first derivative test, meaning that as long as this equation is autonomous, which notice it is, it's a function of y only, then dy dt should always be positive or negative in region 1. So it doesn't matter what value of y I choose. Let's say I chose 1. I'm sorry, y equals 4. Well, in that case, 4 squared is 16 minus 3 times 4. That's 16 minus 12. That's positive 4. So I'm just going to put a positive sign in here. And that positive will just indicate that the rate of change is positive, which means the function in this interval will always be increasing. Between 0 and 3, let's say we pick y equals 1. 1 squared minus 3 is going to give me a negative number. And so that means that on this interval, and then on this third interval, for y is less than 0, we could pick something like y equals negative 1, and negative 1 squared is positive 1 minus 3 times negative 1. That's going to be a positive number. So the function will be increasing for all values of y below 0. But we'll come back to working with this more. I just wanted to give that insight that we can actually do more with autonomous equations just by knowing equilibrium points.